Hi guys, welcome to the lesson of partial differential equation. So we have started second order differential equations, and we talked about the canonical forms, and we talked about classification of second order partial differential equations having two independent variables and more than two independent variables. And we saw how to construct the solution and transformation for canonical forms. So now we are going to start solving some classical partial differential equations. So first of all, we will start with the heat equation. So this heat equation belongs to the great mathematician Joseph Fourier, who defined the equation, modeled the equation, and solved the equation using some initial and boundary conditions using Fourier transforms and Fourier series. So in today's class, we are going to discuss heat equation. So here is the general form of one-dimensional homogeneous heat equation. We can see that dou u over dou t is equals to c squared dou square u over dou x squared. All right, so we are just talking about the transfer of heat in a rod of dimension x. That's why we are calling it one-dimensional heat equation. So we are only interested in the flow of heat in the x direction only. So we know that heat flows from higher concentration to lower concentration, and it diffuses in the material. So in the conductor or in the metal rod. So now we can see that the partial differential equation dou u or dou t, it represents the change in temperature with respect to time, and then on the right hand side we have the second partial derivative with respect to x. So we have some constant that is c squared. It's a thermal diffusivity, and it's sometimes also denoted by T. So you may have seen somewhere equation like this. So it is basically the same thing, right? It may be also written in this form. So now we already talked about the homogeneity and inhomogeneity of partial differential equations. So here we can see that the linear operator, that is LU, is equals to 0. Therefore, we call it homogeneous differential equation, right? And here we can see that LU is equals to some function of the independent variables. So this is inhomogeneous equation. Now we'll talk about some types of boundary conditions, because when we need to find the particular solution of any partial differential equation or any differential equation, we need some boundary conditions, some initial conditions. So let's talk about some types of boundary conditions. So let us consider a rod of length L, where the initial point is point A, this point, and the final point is point B, and heat flows from point A to B. So point A and point B are basically called the boundaries, right? So here we have x is equals to 0, the starting point, and here we have x is equals to L, the ending point, right? So we will have some boundary conditions in this form. U of 0, U temperature at the 0 end and temperature at the end L, right? So first of all, we will talk about Drichlet boundary conditions. So when the boundaries are prescribed, when the boundaries prescribes a value to the dependent variable, right? Dependent variable, which is U, that is temperature in this case. So U of 0 comma t is equals to A, and U of L comma t is equals to B. So A and B may be any arbitrary constants, and their value may be defined in terms of constants like 1, 2, 3, 4, or any real number. All right. So we can write that A, B belongs to real numbers, right? So, and if A, B is equals to 0, then the boundary conditions are called homogeneous boundary conditions. Otherwise, in this form, if there are any constant other than 0, then they are called inhomogeneous boundary conditions, right? So homogeneous boundary conditions may be written in this form: U of 0 comma t is equals to 0, U of L comma t is equals to 0. So these are homogeneous boundary conditions. Then we have Newman boundary conditions. Newman boundary conditions, the derivative of dependent variable is known for all parts of the boundary. All right, so in this type of boundary conditions, we will be given with derivatives at the boundaries, right? Derivative of the dependent variable with respect to x at and 0, at and 0, and at and L, right? So we can see that they are the derivative boundary conditions. So these are Newman boundary conditions. And again, if A and B are 0, then these are homogeneous. These may be written like this in the homogeneous form: U of x at x is equals to 0 is equals to 0, and U of x at x is equals to L is equals to 0, right? So they may be given in this form. So these are the Newman boundary conditions, that are the derivative boundary conditions. And then we have Robin boundary conditions. Robin boundary conditions are the weighted sum of Drichlet and Newman boundary conditions. So we can see that they are in the sum form. This is a Drichlet boundary condition, and this is a Newman boundary condition. And when we sum up the Drichlet and Newman, that is equals to some constant, then we call it as Robin boundary condition, right? And again, if A and B are 0, then these are homogeneous boundary conditions. Then we have Cauchy boundary conditions. Cauchy boundary conditions corresponds to imposing a Drichlet and Newman boundary conditions simultaneously. So one of the boundary condition will be a Newman boundary condition at x is equals to L, or x is equals to 0. And similarly, the other boundary condition will also be at x is equals to L, or x is equals to 0. So this may be should be similar, right? If it's 0 here, then it should be 0 here. If it's L here, then it should be L here, right? So these are equal to constants alpha and beta. And again, if alpha beta are 0, then these are homogeneous. Otherwise, these are inhomogeneous boundary conditions, right? Then we have mixed boundary conditions. So mixed boundary conditions are basically Drichlet boundary conditions are prescribed in some parts, and Newman boundary conditions are prescribed in some parts. So you can see that here U of 0 comma t is equals to A, and here U of x comma U of xl comma t is equals to B, right? So what's the difference between the Cauchy and mixed boundary condition is that in Cauchy boundary condition, this value should be same, But here you can see in mixed boundary conditions, these are different. This is at x is equals to 0, and this condition is at x is equals to L, right? So these are the boundary conditions. And if we uh, want to interpret these, so we can say that u of 0 comma t, if u of 0 comma t, let's say at point 0 at x is equals to 0, if this temperature is 0, and at point x is equals to L, temperature is some constant B, then we might say that the end A is kept insulated, and at end B we are giving some constant heat, right? We are providing some constant heat. So this is the interpretation of these boundary conditions. Now we are moving towards the solution of the heat equation. So we will use method of separation of variables. There are many other methods like uh, transform methods, Fourier transforms, Laplace transforms, and eigenfunction expansion, Duhamel's method, and there are many other methods for solving these equations. But now we will talk about method of separation of variable first, right? Then we will go to other methods as well. Now let us consider a heat equation is given, one-dimensional heat equation is given, and we need to find the general solution of this equation. So we need to separate the variables first. So here we are going to separate variables. We are saying that like let u of x comma t is equals to x t, right? Where x is a function of x and capital T is a function of t. So if we differentiate this u partially with respect to x, we will get x prime t. And when we will again differentiate this partially with respect to x, then we will get x double prime t, right? Because t will be treated as constant as we are differentiating with respect to x partially, right? In similar manner, when we will differentiate u with respect to t partially, then we will get xt prime. So we will put these derivatives in equation 1. That is dou I u over dou t is equals to c squared dou I square u over dou x square, right? So we'll plug in the values of dou I u over dou t and dou I square u over dou x square respectively. So we'll get uh, here xt prime in place of dou I u over dou t, and c square times x double prime t in place of c square dou I square u over dou x square, right? So we will separate the variables x with x and t with t. Here you can see that we have separated the variables, and now these equations will be converted into second order and first order ordinary differential equations. And we know that these are the two ratios. So therefore, there exists a constant lambda such that these ratios are equal to lambda, right? Now, if both the ratios are equals to lambda, then they are independently equal to lambda also, right? So here we write in this form. Now the form of the solution depends on three cases, right? So lambda may be 0, or lambda may be positive, or lambda may be negative. So these are the three cases for lambda, right? We'll consider all three cases because initially we don't know either lambda is 0, positive, or negative, right? So we'll consider all three cases, and then we will use the principle of superposition to find the general solution, right? So using first case, when lambda is equals to 0, So this x double prime over x will be equals to 0, and similarly this one is 1 over c squared t prime over t will be equals to 0. Here we will solve the equations. This is a second order homogeneous differential equation. This is a first order homogeneous differential equation. We will make the auxiliary equations. The auxiliary equation of this equation, say this is equation 1, say this is 2. So the auxiliary equation of 1 will be r square is equals to 0. It means that the roots are 0 comma 0. So the solution of this ODE will be x is equals to c1 times x plus c2, and solution of this first order ODE will be simply t is equals to c3, right? So this t prime basically means dt over dt, right? So is equals to 0. So when we will integrate this, we will get t is equals to c3. And similarly for this one, right? So this is basically this x double prime means dx d square x over dx square, right? So when we will integrate this twice, or we can directly find the solution by integrating this equation twice, or we can use auxiliary equation, right? We have been doing in the part of ordinary differential equations. Now we have the solution. So now initially what we consider was u of xt is equals to xt, right? So this is equals to c1x plus c2 times c3. Here u x comma t is equals to c3 times c1x plus c2, right? When lambda is equals to 0. Now we move to the second case, which is lambda is greater than 0. So if lambda is greater than 0, it means that it is always positive. So we'll use p square to uh, determine that this value is always positive, because whatever value we will give to p and it's a square, so it will make it positive, right? So that's why we are using lambda is equals to p square. And we will solve the ODE. Similarly, you can see this is a second order differential equation. This is a first order differential equation. In the similar manner, we can solve using the auxiliary equations. Here, the auxiliary equation will be r square minus p is equals to 0. So r is equals to plus minus p, two roots. That is, one root is p and second root is negative p, right? So here is the solution. And here the root is p square. So this will be the solution, right? Sorry, it will be not p square. In fact, this will be c square p square, because it's c square p square, right? So this will be the solution for both ODEs. Now we will multiply them as we supposed initially, that u is equals to xt. Therefore, we will multiply x by t. So x is this function and t is this function. So their product will form the solution for uxt. Now we'll consider case 3, where we said that lambda is equals to 0 for. So now we can say that if lambda is equals to lambda is less than 0, sorry. So lambda is equals to negative p square, right? So this will be always negative, because p square will make p always positive, whatever value we give to it, either negative or positive, but this negative sign will make it negative. That's why we write it in this way, right? So again, this is a second order differential equation, this one, and this is first order differential equation, right? So now the roots of this differential equation will be imaginary roots, right? R is equals to plus minus p iota, and the roots for this equation will be negative c square p square. We will construct the solution. Because of these imaginary roots, the solution will be in the form of sine and cosine. So this is the solution for x, c7 cos px plus c8 sine px, and this is solution for t. We'll write in the product form, as we considered that u is equals to xt, so we multiplied x by t. This is the function of x, this is the function of t, right? So we write in the product form. Now we can use boundary conditions to find these constants C1, C2, C3, C4 to C9. And for that, now we are applying some boundary conditions, and we will start with the Drichlet boundary conditions. In fact, homogeneous Drichlet boundary conditions, there are the basic boundary conditions, and these conditions are used very much, right? So u of 0 comma t is equals to 0, and u of L comma t is equals to 0. So these are the Drichlet conditions, and this is the initial condition, that is t is equals to 0. That's why we are calling it initial condition, and that is equals to some function of x. It may be any function of x, maybe sine x, cosine x, x squared, or any function of x, piecewise function. It may be any piecewise function, right? So it may be any function of x. Now we will apply the boundary conditions on all three cases respectively. So in the first case, we get this solution, right? U of x comma t is equals to c3 times c1x plus c2. When we will apply the boundary condition, u of 0 comma t is equals to 0, this implies that this is equals to 0, right? So everywhere for x, we will put 0, right? Because this shows that x is equals to 0. Then we can see that this C3 cannot be equals to 0, because if this C3 is equals to 0, then the whole solution will be equals to 0. Without finding C1 and C2, we cannot assume that this C3 is equals to 0. So we'll find C1 and C2 first. So if C3 is not equals to 0, then it means that C2 is equals to 0, right? So when C2 is equals to 0, now the solution will be left only C3 times C1x, right? Now we will apply the second boundary condition. So second boundary condition is u of L comma t. It means that x is equals to L this time. So we will place L in the place of x. We will plug L. So C1 times L is equals to 0. Again, C3 cannot be equals to 0. Therefore, C1 is equals to 0. So if C1 and C2 both are equals to 0, then u of x comma t will be equals to 0, because initially the solution was u of x comma t is equals to c3 times c1x plus c2. If these both are 0, then u of xt is 0, right? So u of xt is 0. Then we will consider the second case. So the solution for second case was given by this. Now we will apply the initial conditions respectively. First u0 comma t. So for u0 comma t, we will place x is equals to 0 everywhere. So this will be c4 plus c5 times c6 e to the power p square c square t is equals to 0. And here it will be x is equals to L. So this function will be c4 e to the power pl and c5 e to the power negative pl, right? So now we can use these two equations, this and this, to find c4 and c5. We will solve simultaneously. We will get c4 and c5 0. So again, u of x comma t is 0. So again, we have a trivial solution, right? This is called trivial solution when u of x comma t is equals to 0. So in case 1, also we have trivial solution when lambda is equals to 0 and when lambda is greater than 0. So in both cases, we found the trivial solution. But we need a non-trivial solution, right? To express the temperature, that is ux comma t, right? In terms of some function. So now we will consider case 3 and apply it similarly, that x is equals to 0. So when x is equals to 0, it will be c7 times cosine 0 plus c8 times sine 0. So cosine 0 is equals to 1 and sine 0 is 0. So we will be left with the c7 times c9 e to the power negative p squared c squared t is equals to 0. So again, c9 cannot be equals to 0, because if c9 is 0, then the whole solution will be 0, right? So that's why we are taking c7 is equals to 0. Now if C7 is equals to 0, we will be left with only C8 sine n pi x over L times C9 e to the power negative p squared c squared t, right? So this will be ux comma t. Now we will apply the second boundary condition, that is at x is equals to L. Again, it says that is equals to 0. So C8 sine PL, sorry, this is not sine n pi x over L. This is sine px. All right. So now we will apply L in place of this x. So it will be C8 sine PL times C9 e to the power negative p square c square t is equals to 0. Again, C9 cannot be equals to 0. All right. Keep in mind C9 is not equals to 0. This constant will never be equals to 0. We will not treat it as 0, right? For the boundary conditions, because the boundary conditions are actually the boundary conditions of x. So we are solving for the constants of x, right? Therefore, sine PL is equals to 0. It means that PL is equals to sine inverse 0, and sine inverse 0 is 0, uh, pi, 2 pi, 3 pi, and so on. So generally, we can say that sine inverse 0 is n pi, because sine n pi is 0, right? So we'll write n pi in place of sine inverse 0. So P will be equals to n pi over L. Now we'll plug the value of this P in the equation. So we will get C8 times sine n pi x over L, C9 times e to the power negative n pi c over L whole square times t. And remember that C7 is already 0. Here we calculated C7 and it's equals to 0. So it will not appear in the solution now, right? So now we are only left with this form after applying the boundary conditions. Now we can say that this C8 times C9 is a product of two constants. So we can write a product of two constant in a summation form, right? So we will write it sum n is equals to 1 to infinity bn, right? We are saying that this product of these two constants is equals to a sum of a summation of a series, right? So we can write it like that. Now we will use superposition principle to add all the three solutions. So we talk about three cases. So actually there are three solutions, but two are the trivial solutions for lambda is equals to 0 and lambda greater than 0. We get trivial solutions, right? And in case of the homogeneous Drichlet boundary conditions, we will always get this trivial solution for these two cases, lambda is equals to 0 and lambda greater than 0. So you'll only left with the solution for lambda is less than 0, that is this solution, right? So what we did, we just replaced this C8, C9, the product with this sum. Here you can see that, and the rest is the same. So we will only left with this solution, and this is the general solution of a heat equation, right? This is the general solution of a heat equation. Now, if you find a particular solution for this equation, we need some initial conditions. So let's say that our initial condition ux of 0 is equals to some function of x is given. So we will apply t is equals to 0 in the equation. So here e to the power is, it will be e to the power 0 because it was e to the power negative n pi c over L times T, and when we will plug 0 for T, it will be 0. This is 1. So we'll only left with this. And remember that this is a Fourier sine series, right? We know that Fourier sine series is represented by this form, right? Bn sine n pi x over L. So we know that how to find the coefficient of this Fourier sine series. We will use the integral of Fourier series. So the coefficient of Bn for Fourier series is equals to 2 over L, 0 to L f of x sine n pi x over L. So this is basically half range Fourier series, right? So we are only calculating the sine series because in the equation we have sine series, right? If we have cosine series in some other problem, so we use cosine series, right? So but here we only have sine series, so we are using sine series. So we will only calculate the coefficient of sine series, that is Bn. So we know that Bn is equals to 2 over L, 0 to L f of x times sine n pi x over L dx, when x is between 0 to L, right? This is the period, this is called the period. So P is equals to L here. Therefore, we plug in L and n pi x over L here, right? So now we can replace Bn with this integral, and we can write the journal form more precisely, right? So now if a function of x is given, initially if some function is given, f of x, let's say it's x or some function, so we can solve for it. Let's say f of x is given as x, right? So we'll calculate this integral by using by path rule. So here is the solution of this integral. You can see that 2 over L is common, that will be outside, and the rest of the integral will be solved using by path rule. Then we will apply the limits from 0 to L, and you all are well familiar with this Fourier series, and you can solve this Fourier series easily, and the end result will be Bn will be equals to negative 2L over n pi times negative 1 power n, right? And then we can shift this negative sign to the bracket, then we will write n plus 1 in the power. So we get Bn. Now we can replace the integral with this part only, because this is the solution of the integral for f of x is equals to x, right? So now this is the particular solution for this initial condition. So this is the solution of heat equation. So we can find the temperature at any point in the rod. This is rod from, let's say if L is equals to 1. So we can place 1 instead of L here, right? And if we want to calculate temperature at x is equals to, let's say 1 over 2, then we will put 1 over 2 instead of x everywhere, and let's say we want to calculate at x is equals to half and t is equals to 2 seconds. So we can calculate the temperature from this equation at any point in the rod at any time, right? So this is the basic idea of the heat equation. We need to find the temperature, and temperature depends on the two independent variables, that is x and t, right? So this is the particular solution to the homogeneous heat equation, one-dimensional with homogeneous Drichlet boundary conditions. Now if we are given with this initial condition, let's say u of x comma 0 is equals to negative sine 2x, plus 3 over 2 sine 3x. So now f of x, this is basically f of x, right? And let's say that c is equals to 1. So what we need to do is, first of all, we will generate the sine series, Fourier sine series for this function. As we already said that uh, bn is equals to 2 over pi from 0 to pi negative sine 2x plus 3 over 2 sine 3x sine nx, right? So now here this integral is the integral of sines, right? So we know that uh, here it's n, right? So n is basically equals to 1, 2, 3 to so on, right? So we will get only value when this n is equals to 2, because here it's 2x, right? And n is equals to 3 because of this 3x. Otherwise, all n's will, the integral of other all n's will be 0, right? So all other bn's will be 0. We will only get the values of b2 and b3. So b2, the value of b2 will be equals to -1, the coefficient of this, and b3, because of this 3 here, it's n is equals to 3, here it's n is equals to 2. So b3 will be equals to 3 over 2, the coefficient of this sine 3x, right? And all other bn's will be 0. So now we can write the heat equation in this form. All other bn's are 0, so we will always have this b2 and b3 only, right, in this situation. So we can write negative sine 2x e to the power -4t plus 3 over 2 sine 3x e to the power -9t, right? What we did is we just plug 3 over 2 in place of n, right, in the original equation, that is in this equation. Right? That is in the form of f of x here in this equation, right? So f of x was given negative sine 2x plus 3 over 2 sine 3x. So we calculated the values, and you only get the values for b1 and b2 and b3. So for b2 here, first we will plug n is equals to 2. For b2, n is equals to 2 because this shows n, right? And c is given 1, so it will be 1. And for b3, similarly, it will be, this n will be 3, right? So for b2, it's n squared, that's why it's 4. And for b3, it's n squared, and 3 squared is 9, right? And this pi will cancel with pi, because we are saying that now the length is from 0 to pi, right? Here we have said that length is from 0 to pi, so we'll place pi in the place of L. So this L will cancel out with pi, right? So we can write here pi, because it's the general solution, so we can write pi here, because now we are talking about pi and pi here, pi and pi. So these will cancel out each other, right? Pi, because we have taken L as pi in this question, right? So this is the solution for this question. A to the power -4t, c is 1, n is 2 for this, and c1, n is equals to 3 for this, right? So in this way, we got the final answer for this heat equation. And similarly, we can be given with a initial condition in a piecewise form, right? So we know how to solve this piecewise function, how to generate the Fourier series. We will integrate this piecewise and we will get the Pn, whatever the Pn will be, we will place here, right? In this form, we already know that the solution is given in this form, Bn sine n pi x over L e to the power negative n pi c over L square t, right? So here we can see that period is from 0 to pi. It means that is equals to pi, and it means that L is equals to pi basically, right? So we can plug pi instead of L here. So again, this will be cancelled and we're left with nx, right? And here nc whole square t. So we can generate the solution for this initial and boundary value problem. So hope you guys understood this Drichlet homogeneous boundary conditions, the solution of one-dimensional homogeneous heat equations for Drichlet boundary conditions. Now, in the next video lesson, we will talk about the inhomogeneous Drichlet boundary conditions for one-dimensional homogeneous heat equation. All right, so thanks for watching.